Tonight, we're going to explore something that cannot be seen, cannot be touched, and has never once been directly detected by any instrument ever built. And yet without it, you wouldn't exist. The galaxy you live in wouldn't exist. In fact, the universe as we know it, every star, every planet, every atom of ordinary matter, would never have formed at all. What we're talking about is dark matter. Scientists have determined that it makes up roughly 27% of everything the universe contains. Ordinary matter, everything you have ever seen, touched, or measured, accounts for just 5%. The rest is dark energy, a mysterious pressure slowly pushing the universe apart at its largest scales, and dark matter quietly, invisibly, holding everything together from within, 5%. Think about that for a moment. Every telescope ever trained on the sky, every probe ever launched from this planet, every star ever charted, every nebula ever photographed, every galaxy ever catalogued by every observatory ever built, every element on the periodic table, hydrogen, carbon, oxygen, iron, gold, every atom in every rock and every ocean and every living thing that has ever existed on this planet. All of it. The entirety of what we have ever seen or touched or understood, 5% of the total content of the universe. The other 27% is invisible. It does not emit light, it does not absorb light, it does not interact with atoms in any way our instruments can measure. It passes through the densest materials we know as though they do not exist. And yet it is the reason the universe has the structure it does. It is the reason galaxies form at all. It is the reason the cosmic web, the vast architecture of filaments and voids and clusters that spans everything we can observe, exists in the first place. It is, in the deepest sense, the reason we are here. Here's the thing most people don't realize. Dark matter isn't simply a puzzle scientists are working to solve. It isn't a gap in a ledger, an annoying discrepancy to be cleaned up by future observations. It is the skeleton the universe was built on, the gravitational scaffolding that shaped the first concentrations of matter in the early universe, long before a single star had ever ignited. Without it, the early universe, already expanding, already thinning, matter spreading thinner and thinner across growing distances, would have remained an almost featureless fog. No great filaments drawing matter into streams, no collapsing clouds giving birth to stars, no galaxies, no stars, no planets, no chemistry, nothing that could give rise to anything like life. And yet we cannot see it. We cannot touch it. We only know it is there because of the shadow it casts on everything around it. That is quietly one of the most extraordinary and unsettling facts in all of science, that we live inside something we cannot perceive, that the structure we do see, the luminous, bright, atom-built universe that has absorbed all of human attention and filled every observatory catalogue ever produced, is the minority, the 5%, the lit fraction of something much larger and far more dominant that remains permanently, stubbornly invisible. And by the end of tonight, you're going to understand exactly why. Before we dive in, and if you're the kind of person who finds yourself drawn to questions like this one, consider subscribing. It keeps this channel alive and puts these videos in front of others who are looking for exactly this. Now, let's begin. For most of human history, we assumed the universe was made of what we could see. That assumption felt entirely reasonable. It wasn't laziness, it wasn't a failure of imagination. It was genuinely the only logical starting point available. You look up at the night sky and you see stars, hundreds on a clear suburban night, thousands from somewhere dark enough, On a truly dark night, far from city lights, you can see the Milky Way itself, a luminous river of light arching across the sky, the combined glow of hundreds of billions of stars too distant and numerous to resolve individually. The universe is obviously made of this: light, stars, matter you can see and count and measure. This assumption deepened as astronomy developed more powerful tools. In the centuries after Galileo first turned a telescope to the sky in 1609 and found Jupiter's moons and the phases of Venus, astronomers built progressively larger and more sensitive instruments, and each generation found more of the same thing at ever greater distances. Stars organized into clusters, glowing clouds of gas, nebulae that resolved, with better instruments, into stellar nurseries where new stars were being born. And beyond those, faint smudges of light that lay at the edges of visibility and provoked genuine controversy about their nature. Were those smudges clouds within our own galaxy, or were they entire separate galaxies, each containing billions of stars located at unimaginable distances beyond the Milky Way? This question was debated formally in what became known as the Great Debate, held at the Smithsonian Institution in Washington on April 26, 1920. Two of the leading American astronomers of the era, Harlow Shapley and Heber Curtis, argued opposing positions before a professional audience. Shapley contended that the spiral nebulae were within our galaxy, relatively nearby clouds of gas. Curtis contended they were separate island universes, vast stellar systems like the Milky Way, located at distances so immense they dwarfed anything previously imagined. Neither man had definitive data in hand that day. The debate ended without resolution. What ended the uncertainty in the years that followed was the work of Edwin Hubble at the Mount Wilson Observatory in California, using the 100-inch Hooker telescope, the most powerful telescope in the world at that moment, by identifying a particular type of pulsating star called a Cepheid variable within the Andromeda Nebula, a star whose pulsation period precisely indicated its intrinsic brightness and whose apparent faintness thus directly revealed its distance. Hubble placed Andromeda far beyond the boundaries of the Milky Way. The distance he calculated in 1924 was roughly 900,000 light-years. The Andromeda Nebula was, as Curtis had argued, an entirely separate galaxy. The universe was far, far larger than even those who had imagined it might be large had quite prepared themselves to accept. That was the first expansion of our picture of the universe. It would not be the last. In 1929, Hubble went further. He measured the distances and the recession velocities using the Doppler redshift of their light of dozens of galaxies across a range of distances, and he found a relationship that astonished the entire scientific community. The farther away a galaxy was, the faster it was receding from us, not by coincidence, not approximately, precisely as a function of distance. The universe was not simply large and old and static. It was expanding, every galaxy moving away from every other, the distances between them growing with time. Running that expansion backward in time implied that everything had once been in a single, extraordinarily dense and hot state, a state from which everything we see had exploded outward. The Big Bang. By the middle of the 20th century, the picture of the universe had been transformed almost beyond recognition from what anyone in 1850 had imagined. The universe was roughly 13.8 billion years old. It contained hundreds of billions of galaxies, each containing hundreds of billions of stars. It was not static but expanding. It had originated in an extremely hot, dense state. And all of this, every galaxy, every star, every planet, was made of atoms, protons, neutrons, and electrons, arranged in the 118 configurations we call the periodic table of elements. That atomic picture was itself a triumph of extraordinary precision. In the early decades of the 20th century, physics had explained the periodic table from first principles. Each element was defined by its atomic number, the count of protons in its nucleus, the properties of every atom, how it bonded with others, what colors of light it absorbed or emitted, how it behaved in chemical reactions, followed with mathematical exactness from quantum mechanics and the arrangement of electrons in shells around the nucleus. Every substance in the universe, from the simplest hydrogen atom, a single proton orbited by a single electron, to the most complex molecule in a living cell, was at its root just protons and neutrons and electrons arranged in different configurations. The universe was large, it was ancient, it was complex and strange, but it was, at its most fundamental level, made of stuff we understood: atoms, matter with mass and charge and definite properties, matter that interacted with light, that could be detected and measured and catalogued. Everything that existed was, at least in principle, visible and knowable. That assumption was about to begin to crack. The first person to notice something seriously wrong was a Dutch astronomer named Jan Oort. In 1932, Oort was studying the vertical motions of stars in the Milky Way disk. Stars in the galactic disk don't orbit in perfect circles through a flat plane. They oscillate. They rise above the plane of the galaxy, pulled back down by the gravitational attraction of the disk, pass through and continue below, then rise again on the other side. Slow, enormous oscillations taking hundreds of millions of years to complete, like the slow bobbing of swimmers on a gentle swell. The rate and amplitude of those oscillations, how far above and below the plane the stars traveled, how fast they moved, depended directly on the gravitational strength of the disk pulling them back. And that gravitational strength depended on how much mass the disk contained. Oort measured the vertical motions of stars carefully, derived the implied gravitational force from them, and converted that into a mass estimate for the local portion of the galactic disk. Then he compared that implied mass to the mass he could estimate by counting and measuring all the stars and gas he could see. The numbers didn't match. The motions implied roughly twice as much mass as the visible stars and gas could account for. Something was in the disk that wasn't glowing. Oort noted the discrepancy carefully in his 1932 paper and speculated about what might account for it: dark stars, dead stellar remnants, undetected cold gas, objects too dim to see at those distances. He did not press the point hard. He filed it as a problem for future astronomers with better instruments. He was right that there was something there. He was wrong to assume the explanation would be ordinary and simple and soon resolved. The following year, 1933, the problem appeared at a much larger scale, and with a result so extreme, it should have been impossible to ignore. Fritz Zwicky was a Swiss-American astronomer at the California Institute of Technology and one of the most difficult personalities in 20th century science. He was brilliant, creative, visionary, and socially catastrophic. He insulted colleagues in print with an abandon that would be astonishing even in a less decorous era, once calling fellow astronomers spherical bastards, men who were bastards no matter which direction you looked at them from. But he was right about an extraordinary range of things that the scientific community took decades to acknowledge. He correctly predicted the existence of neutron stars in 1934, years before they were discovered. He correctly proposed that supernovae were a fundamentally different class of stellar explosion from ordinary novae. He correctly predicted that galaxy clusters would serve as gravitational lenses, bending and distorting the light of more distant objects behind them. In 1933, Zwicky turned his attention to the Coma cluster, a rich, dense concentration of more than 1,000 galaxies located roughly 321 million light-years from Earth in the constellation Coma Berenices. He used the Doppler shift in the spectral lines of individual galaxies to measure their velocities along the line of sight to Earth. A galaxy moving toward us has its spectral lines shifted to shorter wavelengths, blue shifted. Moving away, they shift to longer, redder wavelengths. The size of the shift gives the velocity with remarkable precision. It's the same effect you hear when a fire truck's siren changes pitch as it passes, the compression of waves by motion, applied to light instead of sound. The velocities Zwicky measured were enormous. Galaxies in the Coma cluster were moving relative to the cluster's center at speeds of hundreds to more than 1,000 kilometers per second. Individual galaxies at the cluster's edges were moving fast enough that if they were held in the cluster only by the gravity of the visible material, they should have been flying outward into the surrounding void. The escape velocity from a system depends on its mass and its size. Zwicky could estimate both, and the conclusion was stark. He applied a result from classical mechanics called the virial theorem, a mathematical relationship that connects the average kinetic energy of a bound system's components to its average gravitational potential energy. Any system in gravitational equilibrium, a galaxy cluster, a swarm of bees, a gas cloud, obeys it. If you know how fast the components are moving, the virial theorem tells you how much mass must be present to hold the system together. The mass required to hold the Coma cluster together, given the velocities Zwicky had measured, was roughly 400 times the mass implied by the cluster's visible luminosity. The galaxies were moving so fast that the gravitational pull of all the visible stars and gas could not possibly hold them. At those velocities, a cluster with only the mass implied by its light would have dispersed, galaxies flying outward in all directions long before the current age of the universe. The Coma cluster, according to the laws of physics as Zwicky understood them, should not exist as a coherent system. And yet there it was. Thousands of galaxies held together by something. That something was not the visible stars and gas. It had to be something else, something dark. Zwicky published his analysis in a 1933 paper in the Swiss journal Helvetica Physica Acta. He called the missing mass dunkle Materie, dark matter, and proposed it existed in the cluster in quantities far exceeding the visible components. The reaction from the astronomical community was essentially silence. Part of this was Zwicky's reputation. When a person makes enemies as energetically as Zwicky did, people are not always eager to follow up his results. Part of it was genuine scientific caution. Any measurement this surprising is reasonable to treat with skepticism, and the virial theorem analysis rested on assumptions that could be questioned. Perhaps the cluster was not in gravitational equilibrium. Perhaps his velocity measurements were somehow biased. Perhaps there was a mundane explanation no one had quite articulated yet. Most of the scientific community quietly filed Zwicky's discrepancy under the category of things that would surely be resolved by future data, and moved on to other problems, and so began one of the longest silences in the history of science. For more than 30 years, through World War II, through the first radio telescopes, through the dawn of the space age, through the discovery of quasars and pulsars, and the cosmic microwave background, through Sputnik and the moon landings, nobody seriously followed up Zwicky's dark matter result. It sat in the literature. It was not forgotten. It was simply not addressed. Part of the reason was the abundance of other things to discover. The 1950s and early 1960s were decades of extraordinary transformation in observational astronomy. Radio telescopes revealed a universe of sources invisible to optical instruments, supernova remnants glowing in radio waves, the jets of distant galaxies, the first hints of structures that would later be identified as quasars. In 1963, Martin Schmidt identified the redshift of 3C273 and recognized it as an object at cosmological distance shining with an intrinsic luminosity hundreds of times greater than an entire galaxy. The first confirmed quasar, and the first indication that the early universe had harbored objects of almost incomprehensible energy. In 1967, Jocelyn Bell Burnell and Anthony Hewish discovered pulsars, rapidly rotating neutron stars emitting beams of radio waves with such clock-like regularity that the discovery team briefly considered whether the signals might be from an extraterrestrial intelligence. In 1965, Penzias and Wilson detected the cosmic microwave background and handed cosmology its most direct window on the early universe. The missing mass problem, by comparison, seemed like a lesser mystery. It lacked a proposed mechanism, it lacked a theoretical framework that made it urgent, a discrepancy in cluster velocities, even an enormous one, even one published by someone as unmistakably correct about other things as Zwicky was, in the intellectual environment of the 1950s and early 1960s, easy to defer. There were no theoretical tools that made it a pressing problem. There was no obvious way to follow up, and so it waited. Meanwhile, astronomy was transforming. The 1950s and 1960s brought radio astronomy, the ability to detect not just visible light, but radio waves from celestial objects, revealing gas clouds invisible to optical telescopes, mapping the structure of the Milky Way disk through emissions from neutral hydrogen. The 1960s brought the discovery of quasars, enormously luminous objects at cosmological distances, powered by matter falling into supermassive black holes. In 1965, two Bell Labs engineers named Arno Penzias and Robert Wilson detected the cosmic microwave background, the thermal echo of the Big Bang itself, arriving from every direction at a temperature of about 2.7 degrees above absolute zero. The universe was revealing itself to be richer and stranger than anyone had imagined. Every new discovery reinforced the basic picture, a universe made of luminous matter, complex and ancient, but at its root the same atoms and forces everywhere. In this context, the 1960s also saw the beginnings of serious theoretical work on cosmic structure formation, how gravity had turned the nearly uniform early universe into the clumpy, galaxy-filled cosmos we observe. Physicists like P.J.E. Peebles at Princeton and Yakov Zeldovich in Moscow developed mathematical frameworks for understanding how small density variations in the early universe grew under gravity over cosmic time. As they worked through the implications, questions about the total mass budget of the universe became unavoidable. How much matter was there? Where was it? What form did it take? These questions, pressing on theorists from the direction of structure formation, were about to collide with a series of observational results that would make the missing mass problem impossible to ignore any longer. But it was not a theorist who made it undeniable. It was an observer. Vera Rubin's path into astronomy had been complicated by the same professional barriers that made the field less diverse than it should have been. When she applied to graduate school in astronomy at Princeton University in 1948, after completing her undergraduate degree at Vassar College, she was sent a form letter informing her that Princeton's graduate astronomy program did not accept women. She enrolled at Cornell instead, completing a master's degree, and then at Georgetown, earning her PhD in 1954. Her doctoral work suggested that galaxies might themselves be moving in large-scale patterns relative to the universe, work that was received with skepticism and sometimes outright dismissal at professional meetings. She continued regardless. By the late 1960s, Rubin was a staff astronomer at the Carnegie Institution of Washington. Her collaborator Kent Ford had built something remarkable, an image intensifier spectrograph of exceptional sensitivity. Ordinary spectrographs of the era required long exposure times and could only measure the spectra of the brightest parts of a galaxy's core. Ford's instrument was sensitive enough to detect spectra from individual stars and gas clouds across the full face of nearby galaxies, star by star, region by region, tracing the velocity pattern all the way from a galaxy's luminous center to its faint outer edges. In 1970, Rubin and Ford pointed this instrument at the Andromeda galaxy, M31, the nearest large spiral galaxy, roughly 2.5 million light-years away and close enough that individual stars and star-forming regions could be picked out with a large enough telescope. They set about measuring what astronomers call the rotation curve, a plot of orbital velocity versus distance from the galactic center. The expectation was completely clear from first principles. Consider our own solar system. Mercury, the innermost planet, orbits the Sun at nearly 47 kilometers per second. Earth orbits at 30 kilometers per second, Saturn at about 9.7, Neptune, the outermost major planet, at barely 5.4. The orbital speeds drop steadily with distance because the Sun contains almost all the solar system's mass concentrated at the center, and gravitational pull weakens with distance according to Newton's inverse square law. A spiral galaxy, by the same logic, should show the same pattern. Most of a spiral's luminous mass is concentrated in its bright central bulge in the inner disk. Stars further out, far from the bulk of the mass, should orbit more slowly. The rotation curve should peak somewhere near the luminous center and then decline steadily outward, the galactic version of the solar system's pattern. What Rubin and Ford found in Andromeda was a flat curve. Stars at the outer edge of Andromeda were orbiting at essentially the same speed as stars much closer to the center. Rather than declining as expected, the velocity rose from zero at the center, increased to a plateau, and then held there, level, flat, undiminishing, all the way to the outermost measurable region. There was no decline at all. They published the Andromeda rotation curve in 1970. They received modest attention. Some astronomers were interested, many reserved judgment. A single galaxy, however carefully measured, could have unusual properties for local reasons. Perhaps Andromeda was peculiar in some way that wouldn't generalize to all spirals. Perhaps the spectrograph had some systematic error. Perhaps there was a subtlety of the galaxy's dynamics that hadn't been accounted for. Extraordinary results demand extraordinary evidence, and one galaxy, however carefully measured, was not enough. Meanwhile, other observers were reaching similar conclusions from different directions. radio astronomers using 21-centimeter emission from neutral hydrogen gas could trace galaxy rotation curves further into the outer disk than optical spectrographs could reach because the hydrogen extended beyond the visible stellar disk. Morton Roberts and his collaborators had been publishing rotation curves of nearby spiral galaxies through this radio technique. Their curves too were flatter than the Keplerian decline expected from the visible mass distribution. The evidence was accumulating from multiple instruments and multiple techniques, but each result was modest enough to be set aside. What was needed was a systematic, comprehensive survey. What was needed was a result so large and so consistent that it could not be deferred. Over the years that followed, Rubin and Ford extended their work systematically. They selected a sample of spiral galaxies, 21 in total, representing a range of sizes, masses, morphologies, and inclinations to our line of sight. NGC 1035, NGC 2742, NGC 2998, NGC 3672, NGC 4378. Galaxy after galaxy, each measured with the same careful technique across its full extent from nucleus to outer disk. Each one required months of telescope time, careful spectral analysis, systematic error checking. Each result was confirmed before moving on. The result for each galaxy was the same: flat rotation curves. All 21 of them, not approximately flat, not flatter than expected, genuinely, clearly, unambiguously flat. Within observational uncertainties, the outer stars moved at the same speed as the inner ones, galaxy after galaxy, system after system, independent of size or mass or morphology. The phenomenon was not a peculiarity of Andromeda or a systematic error in one measurement campaign. It was, apparently, how all spiral galaxies worked. The implication was the same that Zwicky had drawn from the Coma cluster decades earlier, now arriving from an entirely different direction. Each galaxy contained far more mass than the visible stars and gas could account for, and that mass was not concentrated in the luminous center. It was spread through a vast, roughly spherical envelope extending well beyond the edge of the visible disk, a halo of something. Something that emitted no light and absorbed no light, something that left no direct electromagnetic trace at any wavelength from radio to X-ray, something detectable only through its gravitational pull on the stars and gas around it. Rubin and Ford published the comprehensive 21 Galaxy Survey, co-authored with their colleague Norbert Thonard in 1978. The paper laid out all 21 rotation curves on a single figure, and the pattern was, at that point, simply undeniable. By the early 1980s, the astronomical community had accepted what Zwicky had argued in 1933. Most of the mass in the universe, most of the mass in every galaxy and every galaxy cluster is invisible. We cannot see it. We cannot detect it electromagnetically, but it is there. The question was no longer whether, the question was what. Here is what elevates dark matter beyond a cosmological accounting problem. It is not passive. It did not simply arrive in the universe already distributed and sit there, filling space, contributing its gravity while otherwise doing nothing. It built the universe, physically, structurally, from the bottom up. And we can trace that construction through every one of the 13.8 billion years of cosmic history, from the earliest fractions of a second after the Big Bang to the formation of this solar system and the origin of anything capable of noticing any of this. To understand how, you need to go back to the very beginning. In the first second after the Big Bang, the universe was in a state that has no analogue in ordinary experience. Temperatures were in the trillions of degrees. Densities exceeded anything we find today, even in the cores of the most massive stars. In that environment, the familiar particles of matter, protons, neutrons, electrons, had barely assembled from their constituent quarks. The universe was a single, undifferentiated thermal bath. Photons, neutrinos, quarks, electrons, all interacting constantly, all in thermal equilibrium with each other. There was no structure, no differentiation, no material organization at any scale. Everything was the same everywhere, except for tiny, random quantum fluctuations, regions fractionally denser or less dense than their surroundings by amounts so small they defy ordinary intuition. 1 part in 100,000. That was the amplitude of the density variations seeded in the very early universe by quantum processes. 1 part in 100,000, a difference of density so small that if you had a room full of air at sea level and increased its density by the same fraction, you couldn't detect the difference with any instrument available in 1980. And yet, from those tiny variations, everything you see in the night sky was eventually built. As the universe expanded, it cooled. By the first 20 minutes, the temperature had dropped far enough for a critical process: Big Bang nucleosynthesis. Protons and neutrons fused into the first atomic nuclei. Most of the universe's protons remained as single protons, hydrogen nuclei. About a quarter of the mass went into helium-4, built from 2 protons and 2 neutrons. Tiny traces of deuterium, heavy hydrogen, 1 proton and 1 neutron, and helium-3 and lithium-7 were also produced. Then the temperature fell below the threshold for nuclear reactions to proceed, the process stopped, and the elemental inventory of the universe was fixed. Roughly 75% hydrogen, 25% helium by mass, with the trace elements in quantities measured in parts per million. Think about what that means. There was no carbon, no oxygen, no nitrogen, no silicon, no iron, no calcium, no phosphorus. None of the elements that rocky planets are built from. None of the elements that chemistry requires. None of the elements that biology depends on absolutely. The entire periodic table, from lithium onward, all 115 elements beyond helium, was completely absent from the early universe. The universe in its first hundreds of millions of years was, elementally, almost empty of complexity. Those elements would have to be made later by stars. That hadn't formed yet, but the universe remained opaque for the next 380,000 years. In those 380,000 years, the universe was too hot for electrons to bind to atomic nuclei in stable orbits. The electrons were free, and free electrons scatter photons the same way fog scatters headlights or clouds scatter sunlight into a diffuse grey glow. Light could not travel in a straight line. The universe was a plasma, a hot, churning, glowing medium in which photons were constantly absorbed and re-emitted, trapped in the dense, opaque soup of matter and radiation. In this plasma, ordinary matter was locked in an oscillation that operated on cosmic scales. Gravity was trying to pull matter into denser concentrations. The seeds of future structure were there, in those 1 in 100,000 density variations, and gravity was trying to deepen them. But there was a countervailing force. Every photon in the plasma carried momentum. The dense concentration of radiation pushed back against the gravitational compression with an enormous radiation pressure. Gravity compressed, radiation pushed back. The compression rebounded, the gas expanded, thinned, and then began to fall together again. These were acoustic waves, genuine sound waves, propagating through the plasma on wavelengths of hundreds of thousands of light years, rolling through the early universe in an endless oscillation that had been running since the very early moments of cosmic history. These waves left imprints that we can still read today. The statistical distribution of the wave's amplitude across different length scales is precisely preserved in the cosmic microwave, background radiation, and it is also seen in the spatial distribution of galaxies across the modern universe. The pattern tells us about the competition between gravity and radiation pressure in the early plasma, and critically, it tells us how much dark matter was present. Dark matter experienced none of this oscillation. Dark matter has no electric charge. It doesn't interact with photons at all. Radiation pressure, the force that was sloshing ordinary matter back and forth in enormous cosmic waves, passes through dark matter as though it does not exist. While the photon baryon plasma was oscillating, dark matter was free to respond only to gravity. And so, while ordinary matter was being prevented from collapsing by radiation pressure, dark matter began to quietly accumulate. A region of space fractionally denser in dark matter than its surroundings, when there were such regions, there seeds the same quantum fluctuations that produced the tiny variations in the plasma, had slightly stronger gravity. That excess gravity pulled in more dark matter from nearby. The concentration grew. Its gravity reached further. More dark matter fell inward. Over hundreds of millions of years, dark matter organized itself into the first halos, broad, diffuse, but real concentrations of mass, gravitational wells carved into the fabric of space, while ordinary matter was still oscillating helplessly in the plasma. Here is why this head start matters enormously. When the plasma epoch ended and ordinary matter was finally free to respond to gravity, the dark matter wells were already there. The dark matter had had hundreds of millions of years to get organized. Ordinary matter didn't have to build structure from nearly nothing. It could fall into pre-existing gravitational wells, already deepened, already waiting. Without that head start, ordinary matter would have needed to build its own structure from those same 1 in 100,000 density variations in the face of the universe's ongoing expansion. Structure formation against cosmic expansion is a race. If the expansion is faster than gravity can pull matter together, the density variations never grow. They dilute. With dark matter pre-deepening the wells, gravity wins the race. Without dark matter, expansion wins more often, and the universe remains far smoother than what we observe. Then, 380,000 years after the Big Bang, a transition occurred. The universe cooled below approximately 3,000 degrees, hot by ordinary standards, but cool enough for a critical threshold to be crossed. Electrons slowed enough to be captured by atomic nuclei. Hydrogen and helium atoms formed whole, electrically neutral atoms for the first time. And those neutral atoms did not scatter photons. The fog cleared. The universe became transparent. The photons that had been trapped in the plasma for 380,000 years were suddenly free. They streamed outward in all directions at the speed of light, and they have been traveling ever since. Today, 13.8 billion years after that moment of liberation, those photons arrive at Earth from every direction in the sky. The universe's expansion has stretched their wavelengths enormously from visible light to microwaves, cooling them to a temperature of just 2.725 degrees above absolute zero. They form what we call the cosmic microwave background radiation, the oldest light in the observable universe, the thermal relic of the moment the fog cleared. Arno Penzias and Robert Wilson discovered this radiation in 1965, not by design but by accident, while working with a microwave antenna at Bell Telephone Laboratories in Holmdel, New Jersey. The antenna had been built for satellite communication, and they were trying to calibrate it for radio astronomy. They found an unexplained noise, a persistent, low-level microwave signal, coming equally from every direction in the sky, regardless of where they pointed. They cleaned the antenna, they checked the electronics, they removed bird droppings from inside the horn. The signal remained isotropic, unchanging, inexplicable. When they eventually reached out to Robert Dicke at Princeton, who had been theoretically predicting exactly such a relic signal from the Big Bang, Dicke's reaction was immediate. He turned to his collaborators and said, "We've been scooped." What Penzias and Wilson had found was the first direct detection of the afterglow of the Big Bang itself. Penzias and Wilson were awarded the 1978 Nobel Prize in Physics. The cosmic microwave background has since been mapped in extraordinary detail by a succession of space-based observatories. The Kobe satellite, launched in 1989, made the first all-sky map and detected the tiny temperature variations across the sky, the imprints of those acoustic oscillations in the plasma, winning the Nobel Prize for its principal investigators in 2006. The WMAP satellite, launched in 2001, produced the first high-resolution full-sky map, beginning to reveal the statistical structure of those variations in detail. The Planck satellite, launched by the European Space Agency in 2009 and operated until 2013, produced the definitive map, temperature variations of about 30 millionths of a degree across the sky, resolved with angular precision sufficient to distinguish structures smaller than a degree across. That map is extraordinary. By analyzing the statistical pattern of hot and cold spots, what physicists call the angular power spectrum of the CMB, cosmologists can read off the physical conditions of the early universe with a precision that would have seemed impossible to scientists of the 1960s. The size of the spots, the ratio of the first to the second to the third acoustic peak, the overall amplitude of the fluctuations, all of these encode the density of ordinary matter, the density of dark matter, the geometry of the universe, the age of the universe, the rate of expansion. When those parameters are fit to the Planck data, the dark matter density comes out to approximately 27% of the total energy content. And the fit only works, and the acoustic peak pattern only matches the observed map, if dark matter was already present at 380,000 years of cosmic age, already distributed in specific ways, already having formed the gravitational wells that ordinary matter was about to fall into. Without dark matter in the model, the CMB doesn't work. The predicted acoustic peaks fall at wrong angular scales and wrong relative heights. The overall pattern of fluctuations fails to match what Planck observed. The CMB is, among other things, direct evidence that dark matter existed in the early universe in precisely the quantities we infer from rotation curves and cluster dynamics. Three completely independent lines of evidence, derived from completely different physical processes over different cosmic epochs, arriving at the same answer. Now, follow what happens the moment ordinary matter is freed from the plasma. The hydrogen and helium gas falls into the dark matter halos. In the densest halos, those that have accumulated the most dark matter mass, the infalling gas compresses under its own gravity and heats. In the very densest cores, the temperature and pressure rise to the threshold for nuclear fusion. Hydrogen nuclei begin to fuse into helium, releasing energy that pushes outward against the inward pull of gravity, and a balance is struck. The core of the collapsing gas begins to glow. The first stars ignite. These population 3 stars, the first stellar generation formed from gas that contained nothing heavier than trace amounts of lithium, were almost certainly radically different from the stars we see today. Without heavy elements, gas cannot cool efficiently. Carbon, oxygen, and other metals radiate energy as infrared and visible light when heated, allowing a collapsing cloud to cool and fragment into smaller, lower mass clumps. Without metals, the gas stayed hotter, and more mass accumulated before radiation pressure halted the infall. The result, current theoretical models suggest, was stars of extraordinary mass, perhaps 100 to 300 solar masses in typical cases, with some reaching 1,000 solar masses or more. Think about that scale. The most massive stars we observe today, the blue giants, the hypergiants at the very top of the mass sequence, are roughly 100 to 300 solar masses. They are extraordinarily rare. They burn so ferociously that they exhaust their fuel in a few million years and die in spectacular supernovae. A population 3 star of 1,000 solar masses would have been a thing of almost incomprehensible luminosity, shining perhaps 100 million times as brightly as the sun, visible across distances that defy description, and it would have burned through its hydrogen in just a few million years. These first stars were brief, violent, and transformative. When they died, in supernovae, and possibly in some cases as direct collapses to black holes without a supernova explosion, they scattered their interiors into the surrounding gas. And it was in those deaths that the first heavy elements entered the universe. Carbon, forged in the stellar interiors through the triple alpha process, 3 helium nuclei fusing to carbon in the star's core. Oxygen, nitrogen, silicon, sulfur, calcium, iron, each forged at different stages of the stellar life cycle in different zones of the stellar interior at different temperatures and pressures. These elements were ejected into space as the star exploded, mixing with the surrounding primordial gas and enriching it. For the first time, the universe contained something more than hydrogen and helium. The period of universal simplicity was over. The raw material of chemistry had entered the cosmos. The enriched gas, now containing traces of these new heavy elements, fell into subsequent dark matter halos and formed the next generation of stars and the first galaxies. These were small, irregular, turbulent systems by modern standards, but they were real gravitational structures, real collections of stars orbiting a common center, held together by the dark matter halos they inhabited. Inside those early galaxies, more generations of stars formed and died, each enriching the interstellar gas further. The metals accumulated. The raw material of chemistry grew progressively richer. The dark matter halos themselves were not isolated, they merged. When 2 halos came close enough, gravity pulled them together. Their outer regions overlapped, then interpenetrated, and after a complicated dance of gravitational interaction, they merged into a single, larger halo. The galaxies within them merged too. This hierarchical buildup, small halos forming first, merging into larger halos, the larger halos merging into still larger ones, is the backbone of structure formation as we understand it today, and it produces Over cosmic time, the galaxies and galaxy clusters and superclusters we observe. The dark matter halos are arranged in a cosmic web. In the large-scale structure of the universe, dark matter is not uniformly distributed. It exists in a vast, intricate pattern of filaments and sheets and nodes, with enormous voids between them. Imagine a three-dimensional sponge on the largest scales you can conceive, where the sponge material is dark matter and galaxies, and the empty spaces inside the sponge are voids hundreds of millions of light years across, where almost nothing exists. The Sloan Digital Sky Survey, which began operation in 2000 and eventually mapped the positions and distances of more than 3 million galaxies across a quarter of the sky, revealed the full three-dimensional extent of this structure for the first time. The resulting map is one of the most striking images in modern science, a view of the universe in 3 dimensions, showing great walls and filaments of galaxies stretching hundreds of millions of light years, surrounding enormous voids. The Sloan Great Wall, identified in 2003 from that survey, extends roughly 1.37 billion light years and is among the largest known structures in the observable universe. The Laniakea supercluster, identified in 2014 by R. Brent Tully and his colleagues using galaxy flow velocities, encompasses a volume 520 million light-years across and contains the mass equivalent of 100 million billion suns, of which the Milky Way is a small peripheral member on the outskirts of one of its tributary branches. All of it, every galaxy, every cluster, every filament and wall of the cosmic web, traces the underlying dark matter. The luminous matter followed the dark. The bright 5% settled into structures carved by the invisible 27%. Billions of years before the visible universe acquired the form we observe today. To understand the large-scale structure of the universe is to understand the dark matter distribution. The two are, at the deepest level, the same thing viewed from opposite sides of an impassable window. For decades, even as the dark matter evidence accumulated from multiple independent directions, a principled skeptic had a position to hold. The rotation curves were real, Zwicky's cluster velocities were real, the CMB acoustic peaks were real, the simulations that only produced realistic large-scale structure when dark matter was included were real. But all of these lines of evidence shared a common assumption, that Newton's law of gravity, tested with extraordinary precision in the solar system and in laboratories on Earth, applied equally on galactic and cosmological scales. That assumption was not obviously wrong. It was an extrapolation across many orders of magnitude in scale, and extrapolations across many orders of magnitude are exactly the places where physics sometimes breaks down. What if gravity didn't work the same way on galactic scales? What if it was subtly different, slightly stronger than Newton's formula in certain regimes, in a way that hadn't been noticed in laboratory or solar system tests, but would become important across the vast distances of a galactic disk? This was not a reckless idea. It was a principled, quantitative proposal. In 1983, the Israeli physicist Mordechai Milgrom published a paper proposing exactly this. He called it Modified Newtonian Dynamics, MOND. He added a single parameter to Newton's second law, a characteristic acceleration scale, a 0 equal to roughly 1.2 times 10 to the power of minus 10 meters per second squared. An extraordinarily small number, about 1/10 billionth of the gravitational acceleration at Earth's surface. When the acceleration experienced by an object exceeds this scale, as it does everywhere in the solar system, Newton's law is recovered exactly, consistent with all precision tests. When the acceleration falls below this scale, as it does for stars in the outer regions of spiral galaxies, where orbital speeds are low and the gravitational pull from the galaxy's center is faint, gravity becomes slightly stronger than Newton's formula predicts. With this single modification, Mond could reproduce the flat rotation curves of spiral galaxies without invoking any dark matter at all. Better, it made a quantitative prediction. Given only the distribution of visible stars and gas in a galaxy, Mond's formula predicted a specific rotation curve, and those predictions, tested across dozens and then hundreds of galaxies spanning a vast range of sizes and masses, matched the observed curves. Not approximately, well, remarkably well across the full range of galaxy types where the evidence had been most compelling. This was genuinely impressive and demanded to be taken seriously. Mond had real problems. It struggled badly with galaxy clusters. Zwicky's Coma cluster still had far more mass than Mond could account for from visible matter alone. It had profound difficulty with the large-scale structure of the universe. It lacked a deeper physical motivation. It modified the equations without explaining why the modification should exist, without connecting to any deeper principle of physics. And various subsequent attempts to build a relativistic version of Mond that was consistent with general relativity produced frameworks of considerable awkwardness. But at galaxy scales, Mond remained a legitimate alternative that an honest assessment of the evidence could not entirely dismiss. After 2006, that landscape changed dramatically. In 2006, a team led by Douglas Clough at the University of Arizona published a paper in the astrophysical journal, Letters, with a title that was, by the subdued standards of astronomical prose, unusually direct, a direct empirical proof of the existence of dark matter. The system at the center of the analysis was 1E0657-558, a galaxy cluster system located approximately 3.7 billion light-years from Earth. It is now universally known as the Bullet Cluster. What makes 1E0657-558 special is a collision, one of the most energetic events in the universe since the Big Bang, and one that was still unfolding at the moment of observation, frozen in mid-collision like a high-speed photograph taken at precisely the right instant. Two massive galaxy clusters had collided and were now passing through each other. To understand why this matters, you need to understand the composition of a galaxy cluster. The individual galaxies, the bright spiral and elliptical systems visible in optical photographs, are actually a relatively minor component of the cluster's total mass. Between and surrounding the galaxies, filling the entire volume of the cluster, is an enormous quantity of hot, ionized gas, the intracluster medium. This gas, heated to temperatures of tens to hundreds of millions of degrees by the gravitational compression of the cluster's formation, emits X-rays. Space-based X-ray observatories can map it with considerable precision across the full extent of a cluster. In a typical rich cluster, the hot gas contains roughly 5 times the mass of all the visible stars in all the galaxies combined. The intracluster medium is the dominant component of ordinary matter in a cluster. When the two clusters in 1E0657-558 collided at an estimated relative velocity of roughly 3,000 kilometers per second, about 10 million miles per hour, fast enough to cross the continental United States in under a second, the galaxies and the gas behaved in fundamentally different ways. Galaxies, even close up, are almost entirely empty space. The average distance between stars within a galaxy is measured in light years. The typical distance between stars in the Milky Way disk is roughly 4 light years, meaning that even inside a galaxy, almost all the volume is void. When two galaxies interpenetrate, individual stars almost never physically collide. The galaxies interact gravitationally, tidally distorting each other, exchanging stars, channeling gas into starbursts, but the stars themselves pass through. In a cluster merger, the galaxies of both original clusters penetrate through each other's star fields and continue, their trajectories altered by gravity, but their stars physically unimpeded. The intracluster gas was different. Gas is a fluid. The hot plasma of the intracluster medium carries electric charges, ionized electrons and ions, and when two plasma clouds approach each other at extreme velocity, they interact electromagnetically. The pressure of the infalling gas met the resistance of the oncoming gas. The plasma shocked and compressed. Electromagnetic interactions between the charged particles transferred momentum across the collision boundary, decelerating the gas of each cluster dramatically. The gas piled up in the space between the two sets of galaxies that had already passed through. NASA's Chandra X-ray Observatory, which had been launched in 1999 and became the most sensitive X-ray telescope ever placed in orbit, imaged the aftermath. The Chandra image of 1E0657-558 is stunning even to non-specialists. A bright, bullet-shaped concentration of X-ray emitting plasma is visible trailing behind the smaller subcluster's galaxy group, marking the compressed and shocked gas of the collision. The bullet that gives the system its popular name is the gas core of the smaller cluster, having passed through the larger cluster's gas and created a characteristic bow shock at its leading edge, like the compressed air in front of a supersonic aircraft, but scaled to hundreds of thousands of light years. That was one half of the observation. The other half required a different technique entirely. Gravitational lensing, the bending of light by mass, predicted by general relativity and confirmed observationally in 1919, provides a way to map mass regardless of whether it is glowing or dark. Any mass, visible or invisible, bends the paths of light rays passing near it. When we observe a field of distant background galaxies through a foreground mass concentration, the foreground mass distorts the apparent shapes of the background galaxies subtly but systematically and measurably. Round galaxies appear slightly elongated in directions perpendicular to the foreground mass's pull. Pairs of galaxies show correlated alignment patterns that would not be present in an undistorted image. By measuring these statistical shape distortions across thousands of background galaxies, the technique called weak gravitational lensing, astronomers can reconstruct a map of the projected foreground mass with no assumptions about whether that mass is glowing or dark. Gravity is blind to the electromagnetic properties of what generates it. Weak gravitational lensing is blind to those properties too. It measures mass, all of it, whatever form it takes. Clow's team applied weak lensing to the full bullet cluster system using deep Hubble Space Telescope imaging combined with ground-based observations, producing a map of the projected total mass across the collision. The mass was not where the gas was. The Chandra X-ray image showed the bulk of the ordinary matter piled up in the center of the collision, slowed and compressed between the two galaxy groups that had passed through. But the lensing mass map showed two separate, distinct mass peaks, one on each side of the X-ray gas concentration, coinciding with the positions of the two sets of galaxies that had kept moving after the collision. The mass had passed through. The gas had stopped. Whatever was carrying most of the mass, whatever dominated the gravitational wells of these two clusters, had behaved during the collision exactly like the galaxies. It had passed through without interacting. It felt no electromagnetic braking. It experienced no shock. It continued on, leaving the gas behind, and now the mass was in a different location from the ordinary matter. This is the observation that is essentially impossible to explain with any modification of gravity alone. MOND, and any other theory that makes gravity respond differently to matter, but doesn't include a separate dark matter component, requires the gravitational influence to track the ordinary matter. If most of the ordinary matter is in the center, the gravitational influence should be in the center. It was not. The gravitational influence was where the galaxies were, where something non-electromagnetic had moved to, and not where the gas was. The only consistent explanation was matter that doesn't interact electromagnetically, dark matter, a component of each cluster that had passed through the collision as freely as the galaxies did, because, like the galaxies, it carried no electromagnetic charge. The dark matter was now physically separated from the ordinary matter, spatially distinct from it, in a different location. You could see it on the map. After the bullet cluster paper, similar analyses were applied to other merging cluster systems, MACSJ 0025.4-1222, sometimes called the baby bullet, showed comparable mass-gas separation. A growing sample of merging clusters analyzed with both X-ray observatories and gravitational lensing confirmed the pattern across multiple independent systems. The bullet cluster did not tell us what dark matter is made of. It told us something more fundamental. Dark matter is physically real, spatially locatable, and categorically distinct from ordinary matter. Something that has mass, responds to gravity, and passes through electromagnetic interactions as though they simply aren't there. We still don't know what that something is. The search for dark matter's identity is, in many ways, the story of ruling things out. When the dark matter problem became widely accepted after Rubin's rotation curves and before the bullet cluster, the most conservative hypothesis was the most obvious one. Perhaps dark matter was just ordinary matter that happened to be dark. Not exotic, not unknown, not new, just familiar matter in forms that don't emit light. Brown dwarfs, substellar objects, too small to ignite hydrogen fusion, wandering the galactic halo in the cold and dark. Ancient white dwarfs, the ember remains of dead stars, gradually cooling below detectability over billions of years. Rogue planets, torn from their parent systems. Neutron stars, compact and cold. Stellar mass black holes consuming nothing, pulling no light from their surroundings, sitting in invisible silence. All of it made of the same protons and neutrons as everything else, just not glowing. These were given the acronym MACOs, Massive Astrophysical Compact Halo Objects. The name was partly a product of the era and partly a deliberate contrast with the other leading class of candidate, which had its own opposing acronym. MACOs had one crucial advantage: they were testable. If the galactic halo were full of compact, massive, dark objects, brown dwarfs, black holes, cold white dwarfs, they would occasionally drift in front of more distant background stars. When they did, the compact object's gravity would bend and focus the background star's light, causing the star to brighten temporarily in a precise, symmetric pattern that would be identical at all wavelengths. A star that brightened because of a variable star, an intrinsic pulsation, would show the brightening at some wavelengths more than others, and the brightening pattern would be repeatable. A star that brightened because of gravitational lensing by a foreground compact object would brighten identically at every wavelength, rise and fall in a specific mathematical shape called a Paksinski curve, and would never repeat, because the lensing object would have moved on. The signatures were unambiguous, you could tell the difference. And the rate of microlensing events, how often background stars were lensed, would depend precisely on the number of compact objects in the halo. If the halo were predominantly Machos, you could calculate the expected event rate and test whether the observations matched. Starting in the early 1990s, two large international collaborations did exactly this. The Macho project, coordinated from the Lawrence Livermore National Laboratory, operated a dedicated 1.27-meter telescope at the Mount Stromlo Observatory in Australia. Beginning in 1992, automated photometry systems monitored approximately 11.9 million stars in the Large Magellanic Cloud, one of the Milky Way's two brightest satellite galaxies, 160,000 light-years away, and millions of additional stars in the Milky Way's own central bulge. Every clear night for 7 years, each monitored star had its brightness measured. Every brightening event was flagged, checked, and analyzed for the characteristic microlensing signature. The EROS collaboration, Expérience pour la recherche d'objets sombres, a French team, monitored tens of millions of additional stars in the Magellanic Clouds using telescopes at the European Southern Observatory in La Silla, Chile. Both found microlensing events. The events were real. They passed all the statistical and spectral tests for genuine gravitational lensing by compact foreground objects. But there were far fewer of them than the Macho halo hypothesis required. The event rate observed was consistent with lensing by ordinary known stellar populations, stars and stellar remnants in the Magellanic Clouds themselves, and known stellar populations in the Milky Way disk. The contribution from a dark, Macho-dominated halo was constrained to be very small. Statistical analysis placed tight upper limits. Machos in the broad mass range from roughly 10 times Jupiter's mass up to several solar masses could account for at most a few percent of the Milky Way's dark matter halo. Not the answer. But there is a more fundamental reason why ordinary matter, baryonic matter made of protons and neutrons, cannot be the primary dark matter component, and it has nothing to do with microlensing surveys. Big Bang nucleosynthesis constrains the total baryon density of the universe with extraordinary precision. The amounts of helium-4, deuterium, helium-3, and lithium-7 produced in the first 20 minutes of cosmic history depend sensitively on a single parameter: the ratio of baryons to photons in the early universe, essentially the total amount of ordinary matter relative to the total amount of radiation. The heavier elements are more sensitive to this ratio than the lighter ones. Deuterium, in particular, is destroyed efficiently in stellar interiors, and so the primordial abundance of deuterium is a very clean indicator of the early baryon density. We can measure these primordial abundances today, ancient metal-poor stars formed when the galaxy was young and the interstellar medium had not yet been significantly enriched by stellar generations, preserve the original helium to hydrogen ratio in their surfaces. Pristine intergalactic gas, illuminated by the light of distant quasars at cosmological distances, allows spectroscopic measurements of primordial deuterium abundances in gas that has barely been processed by stars. Those measurements from many independent sources and independent techniques all converge on the same baryon density, roughly 5% of the total energy content of the universe. 5%. The same 5% we observe in the visible stars and gas, nowhere near the 27% that dark matter requires. Whatever dark matter is, it is not protons or neutrons in any form. It does not interact via the strong nuclear force. It did not participate in Big Bang nucleosynthesis, because if it had, it would have altered the abundances of the light elements in ways that are not observed. It is, in the most fundamental physical sense, a different kind of matter from every element on the periodic table. This pushed the search definitively into particle physics. The leading theoretical candidate for several decades has been the WIMP, the weakly interacting massive particle. The description is almost a definition. Massive, having substantial mass, somewhere between roughly 10 and 10,000 times the proton's mass, depending on the specific model. Weakly interacting with ordinary matter via gravity and the weak nuclear force, but not electromagnetism, making it both invisible to light and extraordinarily difficult to detect, not interacting via the strong nuclear force which drives nuclear reactions. What made WIMPs so compelling to physicists was something called the WIMP miracle, a numerical coincidence so precise and surprising that many took it as pointing towards something real in nature. In the 1970s and 1980s, theoretical physicists had been developing a framework called supersymmetry, motivated by entirely unrelated considerations. Supersymmetry is a mathematical symmetry that pairs every particle in the standard model with a heavier superpartner, a supersymmetric shadow particle with different spin. Every fermion gets a bosonic superpartner, and every boson gets a fermionic one. Supersymmetry was not invented to explain dark matter. It was developed to solve the hierarchy problem. The standard model predicts a Higgs boson mass that should be driven to astronomical values by quantum corrections, virtual particles contributing to the mass through quantum loops. Yet the observed Higgs mass is relatively modest at 125 giga-electron volts. Supersymmetric particles cancel those corrections with remarkable precision. Supersymmetry also predicts that the strengths of the three non-gravitational forces, electromagnetic, weak, and strong, converge to a common value at very high energies, suggesting a grand unified theory. These were compelling theoretical reasons to take supersymmetry seriously, independent of any dark matter consideration. But supersymmetry has a remarkable additional property. In the simplest versions of supersymmetric theories, the lightest supersymmetric particle, whatever that lightest particle turns out to be, cannot decay into standard model particles without violating supersymmetry's conservation laws. It is stable. It will exist forever once produced. When physicists examined the properties of this lightest supersymmetric particle, typically the neutralino, a mixture of the superpartners of the photon, the Z boson, and the Higgs, they found it was electrically neutral. It was massive, typically in the range of 100 to 1000 giga-electron volts. Heavy, but within the range accessible to particle accelerators. It interacted via the weak force, And when they computed how many neutralinos would have been produced in the hot early universe and how many would have annihilated with anti-neutralinos as the universe cooled below the threshold for their pair production, the resulting relic density matched the observed dark matter density with astonishing accuracy. This was the WIMP miracle. Particles motivated entirely by a separate theoretical puzzle, the hierarchy problem, produced, in the early universe, approximately the right number to account for the dark matter we observe today. Many physicists took this as a strong hint that supersymmetric WIMPs were the dark matter and that direct detection was only a matter of time and experimental sensitivity. The experimental program that followed was one of the most ambitious in the history of physics. Detecting a WIMP directly requires waiting for the rare event in which a dark matter particle, passing through the Earth in enormous numbers but interacting almost never, strikes an atomic nucleus and deposits a tiny amount of energy. The energy involved is on the order of tens of kilo-electron volts. For reference, visible light photons carry a few electron volts of energy. The threshold for X-rays is about 1,000 electron volts. The energy Chandra's X-ray photons carry to map galaxy clusters is thousands to tens of thousands of electron volts. A WIMP's nuclear recoil energy is in this same range, tiny by particle physics standards, but detectable in the right instrument. The challenge is background rejection. Natural radioactivity from uranium and thorium traces in rocks, walls, and detector materials produces nuclear recoils at similar energies. Cosmic ray muons passing through the detector create secondary particles that could fake a signal. The solution to both problems is to go deep underground, where the rock overhead absorbs the muon component of cosmic rays, and to build the detector from materials of extraordinary purity, often requiring custom refinement of natural xenon or germanium to remove radioactive contaminants at the parts per trillion level. LUX, the Large Underground Xenon Detector, operated from 2013 to 2016 at the Sanford Underground Research Facility, located in the former Homestake Gold Mine in Lead, South Dakota, at a depth of 1,480 meters. Its active target was 370 kilograms of liquid xenon, cooled to about 170 degrees below 0 Celsius, and instrumented with arrays of photomultiplier tubes that could detect the faint flashes of light produced when a particle interacted in the xenon. The entire detector was suspended in a tank of ultra-pure water, providing additional shielding. At the time of its final results, LUX set the most sensitive limits ever placed on the spin-independent WIMP nucleon interaction cross-section across a broad range of WIMP masses. No signal. Xenon 1T operated at the Gran Sasso National Laboratory buried under approximately 1,400 meters of rock beneath the Apennine Mountains in central Italy. With an active target of 2 tons of liquid xenon, roughly 5 times the active mass of LUX, it improved sensitivity by nearly an order of magnitude. Its 2018 results set new records for sensitivity. No signal. Panda X4T operates at the China Jinping Underground Laboratory in Sichuan Province, 2,400 meters beneath the surface, the deepest underground physics laboratory in the world. Its active target of 4 tons of liquid xenon further extends the reach. No signal. The successor experiments, Xenont with 8 tons of active xenon, Lux Zeppelin with 10 tons, continue to push the sensitivity frontier. The parameter space for the simplest WIMP models is now almost entirely excluded at the sensitivity levels that supersymmetric WIMPs were expected to produce signals. The WIMP parameter space has not been completely closed. There remain mass ranges and interaction modes that the current experiments cannot reach. But the simplest, most natural, most theoretically motivated realizations of the WIMP hypothesis have been searched and found empty. Meanwhile, the Large Hadron Collider at CERN has been searching for supersymmetric particles by producing them directly in proton-proton collisions. The LHC discovered the Higgs boson in 2012, the final piece of the Standard Model and a result of enormous scientific significance. But the superpartners that supersymmetry predicts, the squarks and gluinos at the high-energy end, the charginos and neutralinos at the accessible end, have not appeared. At the LHC's full collision energy of 13.6 trillion electron volts, the simplest and most natural supersymmetric theories are now excluded. Physicists have also pursued indirect detection, searching for the gamma rays or other particles that dark matter particles would produce when they annihilate with each other in regions of high dark matter density. The galactic center, where the NFW dark matter density profile predicts its highest values, is an obvious target. The dwarf satellite galaxies of the Milky Way, small, dark matter-dominated systems with very little astrophysical background, are another. The Fermi Gamma Ray Space Telescope, launched in 2008 and still operating, has mapped the gamma-ray sky with unprecedented sensitivity. There is an intriguing excess of gamma-ray emission from the galactic center that has not been fully explained by known astrophysical sources, but no unambiguous, confirmed dark matter annihilation signal has been identified in any system. As the WIMP parameter space has narrowed without detection, other candidates have gained attention and experimental momentum. Axions were proposed in 1977 by Roberto Peccei and Helen Quinn, not to explain dark matter, but to solve a completely different problem called the strong CP problem. Quantum chromodynamics, the theory of the strong nuclear force, contains a free parameter that could, in principle, take any value. If it takes certain values, the strong force violates a symmetry called CP invariance. It would treat matter and antimatter differently in ways that should produce observable effects in neutron physics. But precise measurements of the neutron's electric dipole moment show CP violation in the strong sector to be unmeasurably small, consistent with zero. Why is this parameter so tiny when theory allows it to be large? Peccei and Quinn proposed a new symmetry that dynamically relaxes this parameter to zero. When that symmetry breaks, it produces a new particle, the axion, named by Frank Wilczek. The axion is extraordinarily light. Its mass could range from less than a billionth of an electron volt to somewhat above that, and it interacts very weakly with ordinary matter, primarily through its coupling to photons in strong magnetic fields. It turns out that such particles produced in enormous numbers in the early universe would make excellent dark matter candidates. They wouldn't interact electromagnetically in the usual sense, they wouldn't absorb or emit light, but they could occasionally convert to real photons in the presence of a strong magnetic field, producing a microwave or radio signal detectable in a sensitive resonant cavity. Experiments like ADMX, the Axion Dark Matter Experiment, and HAYSTAC scan narrow ranges of axion mass by tuning a resonant cavity immersed in a strong magnetic field, looking for the faint microwave signal that axion conversion would produce. No detection yet. but only a small fraction of the theoretically viable axion mass range has been searched. Sterile neutrinos, hypothetical heavier cousins of the ordinary neutrinos that barely interact with anything even in the Standard Model, are another candidate. A sterile neutrino would interact only through gravity, making it even more weakly coupled to ordinary matter than a WIMP. If their masses are in the kilo-electron-volt range, they could constitute the dark matter. A possible X-ray emission line at 3.55 kilo-electron-volts, detected in observations of galaxy clusters and the galactic center by multiple independent groups beginning in 2014, could be consistent with the decay of sterile neutrino dark matter at a particle mass of about 7 kilo-electron-volts. The signal has been studied intensively. It remains unconfirmed and debated. Some analyses support it, others do not detect it at the predicted strength. It is an unresolved question. The honest current picture is this: we know dark matter exists with near certainty. We know its abundance to a few percent. We know its distribution in halos from galactic to cosmic scales. We know it is not baryonic matter in any form. We know it is not any particle in the Standard Model of particle physics. And we have not yet directly detected a single dark matter particle in any laboratory or detector on Earth. That is not a failure. That is the frontier. That is what the edge of understanding looks like. Let's bring this closer to home. The Milky Way is a barred spiral galaxy, a rotating disk of stars and gas with a central bar-shaped structure surrounded by spiral arms embedded in a spherical halo of stars and dark matter. You are inside it. You are located roughly 26,000 light-years from the galactic center, in a minor spiral feature called the Orion Arm, a branch between the major Perseus Arm and Sagittarius Arm. From where you sit, looking up on a clear dark night, you see the combined light of roughly 1 trillion stars, most of them so distant and numerous that they blur together into the luminous band we call the Milky Way. That visible structure, the disk, the arms, the glowing nucleus, spans roughly 100,000 light-years from edge to edge, and perhaps more in the outermost reaches. It is, by any ordinary measure, an enormous structure, but the dark matter halo of the Milky Way is far larger. Current estimates, derived from the motions of satellite galaxies, the kinematics of the stellar halo, and the velocities of stars at extreme galactic distances, place the dark matter halo's radius at somewhere between 600,000 and over 1 million light-years, in every direction. The visible disk that contains every star you've ever seen sits inside a dark matter structure 5 to 10 times its diameter in every dimension. The luminous galaxy is a small, bright core inside a vast, invisible sphere. The numbers are striking when you work through them. The total mass of the Milky Way, all matter combined, dark and luminous, is estimated at roughly 1 to 1.5 trillion solar masses. The visible stars contribute perhaps 60 billion solar masses. The interstellar gas and dust, the raw material from which stars form, adds perhaps 10 to 15 billion more. All the matter that emits or scatters light, everything we have ever observed in our galaxy, amounts to perhaps 5 to 8% of the total mass. 5 to 8%. The same fraction as the universe overall. The vast majority of the Milky Way is the invisible halo. That dark mass is what holds the galaxy together, sets the orbital speeds of stars at every radius, defines the gravitational well into which everything else has settled. The visible galaxy is floating inside it like a bright light inside a vast dark room. The dark matter doesn't respect the boundary of the visible disk. It fills the entire halo volume, including the disk itself, including the spiral arms, including the space around this particular solar system, including the volume occupied by the air you are breathing right now and the space between the atoms of every object in reach. At Earth's location, roughly 26,000 light-years from the galactic center and well into the outer regions of the halo where the NFW density profile has fallen significantly below its central peak. The local dark matter density is estimated at approximately 0.3 to 0.4 giga-electron-volts per cubic centimeter. This is a tiny number in laboratory terms, roughly equivalent to the mass of a proton in every few cubic centimeters of space, far less than the density of any gas we could create in even the best vacuum chamber. But the dark matter fills all of space continuously, not just your laboratory, and integrated over the enormous volumes of the galactic halo, it dominates the mass budget completely. The dark matter distribution within the halo follows a specific mathematical profile derived from N-body simulations of structure formation. In the 1990s, Julio Navarro, Carlos Frenk, and Simon White, using increasingly powerful computers to simulate the gravitational evolution of dark matter halos from early universe conditions, found a universal density profile that described the structure of halos over many orders of magnitude in mass. The density rises steeply toward the center of the halo, then falls off in a characteristic way with increasing radius. At the very center in our galaxy, this predicts the highest dark matter densities, exactly what indirect detection searches target when they point gamma-ray telescopes at the galactic center. At our location in the outer disk, we are well into the extended fall-off region, where the dark matter density is much lower than at the center, but far from zero. Now consider what this means for your immediate environment. The Earth orbits the Sun at 30 kilometers per second. The Sun orbits the galactic center at roughly 220 kilometers per second, carrying the entire solar system with it in that great orbit that takes about 230 million years to complete. From the perspective of the dark matter halo, which rotates much more slowly than the disk, the halo is supported by random motions, not ordered rotation. The solar system is plowing through the halo at something like 220 kilometers per second in the direction of the constellation Cygnus. This creates, in principle, a dark matter wind. If dark matter particles exist in the local halo at the density estimates suggest, and if they are moving in random directions with typical velocities determined by the halo's velocity dispersion, then, from our perspective, the particles appear to stream preferentially from the direction of Cygnus, in the same way that a car driving through rain appears to have the rain coming from directly ahead. If dark matter is made of WIMPs in the mass ranges that direct detection experiments have been searching, the implied particle flux at Earth's surface is staggering, anywhere from tens of thousands to hundreds of millions of WIMP particles per square centimeter per second, depending on mass, through your hands as you hold them out, through the book or phone or whatever you are resting, through the mattress and the floor beneath it, through the planet itself, through the rock and iron and nickel of the Earth's interior, through all of it, without stopping, without interacting, continuing on their paths as though none of it existed. They arrive. They pass through everything. They leave without a trace. Not one has ever been caught. This is one of the stranger and more intimate aspects of dark matter. It is not distant, it is not somewhere else in the universe, far away and abstract. It is here. It occupies the same space you occupy. It flows through the room you are in, through the volume of air around you, through the space between the atoms of your body. It is as close and as present as anything can be. And it is completely, permanently, stubbornly invisible to every biological and technological sense we possess. Think about what that means. Every other substance we have ever encountered interacts with matter in some way that makes it detectable. Light registers on our retinas or on photographic plates or on electronic sensors. Sound puts pressure on eardrums. Magnetic fields deflect compass needles. Even neutrinos, the most weakly interacting particles in the Standard Model, produced in trillions by nuclear reactions in the Sun, and passing through the entire mass of the Earth with only one in about 200 billion stopped, are nonetheless detectable in large enough underground tanks of water because they occasionally interact via the weak nuclear force. Even gravitational waves, ripples in space-time geometry itself, first detected in 2015 by LIGO, with amplitudes measured in thousandths of the diameter of a proton, register on kilometer-scale laser interferometers because the physics is understood and the instruments are adequate. Dark matter interacts with the atoms of our detectors even less than neutrinos do. We compensate by building ever larger, ever purer, ever more shielded detectors and waiting with extraordinary patience. The underground xenon experiments, cooled to temperatures colder than the coldest known place in the natural universe, shielded by hundreds of meters of rock, built from materials refined to purity levels measured in parts per trillion, are, in a very real sense, humanity sitting quietly in the dark, waiting for one of an enormous number of invisible particles to tap just once on a single nucleus in a way that can be measured. So far, the tap has not come. The Milky Way's dark matter halo is not static, it is interacting dynamically with its neighbors. The Large Magellanic Cloud, the nearest of the 50-plus satellite galaxies orbiting the Milky Way, is located roughly 160,000 light-years away and is the most massive of our satellites, a small but genuine galaxy in its own right, with about a tenth the mass of the Milky Way. It is embedded in its own dark matter halo. As the LMC orbits the Milky Way, and current evidence suggests it may be on its first close approach, not an established long-period orbit, its dark matter halo interacts gravitationally with ours. The LMC's passage perturbs the outer regions of the Milky Way's dark matter halo, creating a wake of slightly enhanced dark matter density trailing behind the LMC's path. This dark matter wake, a subtle overdensity in the halo, has actually been detected observationally through its effect on the positions and velocities of distant halo stars. The dark matter halo is not a static, smooth sphere. It has texture, it has response. It remembers the paths of objects that have moved through it. The Sagittarius dwarf spheroidal galaxy tells a similar story. This satellite of the Milky Way, once a small, coherent system, has been making repeated passes through the Milky Way's gravitational field over many billions of years, each passage tearing off more of its stars. Those stripped stars now form a continuous stream that wraps around the sky in great loops, detectable as an overdensity of stars with similar velocities spread across a broad arc of the celestial sphere. The Sagittarius stream is one of the most prominent features of the Milky Way's stellar halo, and it marks the path of a galaxy being consumed. The dark matter from Sagittarius is being stripped and mixed into our own halo along the same paths. The Milky Way's halo is not pristine. It carries the remnants and the matter of every smaller system it has accreted over its history. The Milky Way belongs, in turn, to a larger structure. The Local Group, a gravitationally bound collection of roughly 54 galaxies spread across a volume about 10 million light-years in diameter, dominated by two large spirals, the Milky Way and the Andromeda Galaxy, 2.5 million light-years apart. Andromeda, M31, the most distant object visible to the naked eye on a clear, dark night. Faintly visible in the constellation Andromeda as a ghostly smudge, is slightly larger than the Milky Way and has its own dark matter halo of comparable size. The dark matter halos of the Milky Way and Andromeda are already overlapping. The outer edges of the two halos interpenetrate across the space between them, even though the visible disks are separated by 2.5 million light-years. In roughly 4 to 5 billion years, the two galaxies will collide and merge. This is not a remote possibility or a speculation. It is the result of detailed gravitational modeling of the Local Group, confirmed by measurements of Andromeda's radial and transverse velocities from Hubble Space Telescope proper motions. The galaxies are falling toward each other at roughly 110 kilometers per second. The merger will begin with the two dark matter halos, already overlapping, merging first into a single, larger halo. The visible disks will take longer, making multiple close passes over perhaps 1 billion years before the two disk components settle into a single merged system. That merged system, a large elliptical galaxy, no longer a spiral, sometimes called Milkomeda in discussions of the future, will contain the same total mass, but in a fundamentally reorganized form. Our solar system will almost certainly survive intact, its orbit shifted to a new position in the merged galaxy. But the Sun and Earth will not be harmed by the merger itself. Now, trace the chain backwards. When the Milky Way was young, 12–13 billion years ago, the dark matter halo was already present. It had been accumulating since hundreds of millions of years after the Big Bang, growing from the quantum fluctuations that seeded the cosmic web, building through the aggregation of smaller halos into larger ones, growing through mergers and accretions over billions of years. By the time the first generation of population 3 stars died in the proto-galactic environment that would become the Milky Way, a dark matter halo was already there, not fully grown to its present size, but real, massive, gravitationally dominant. That halo drew in the surrounding primordial gas. Hydrogen and helium fell inward along its gravitational gradient. The infalling gas carried angular momentum, a slow, large-scale rotation inherited from the surrounding cosmic flows, and as it compressed inward, conservation of angular momentum caused it to spin faster. A disk formed, settled into the gravitational plane of the halo, and became the site of successive generations of star formation. Inside that disk, over billions of years, stars formed and burned and died. Metal-poor, population 2 stars in the early Milky Way seeded their surroundings with the first heavy elements when they died. Each generation enriched the interstellar medium further: carbon, oxygen, silicon, iron, calcium. The raw material of chemistry accumulated gradually over generation after generation of stellar life and death. About 4.6 billion years ago, in what is now the Orion Arm, a molecular cloud, cold, dense, enriched by billions of years of stellar cycling, crossed a threshold. It collapsed. At the center of the collapse, a protostellar disk formed around a growing protostar, and the protostar ignited. the disk accreted material and organized into a system of rocky and gaseous planets. The third planet from the center formed at a distance where liquid water was stable at the surface. You exist because of a chain of causation that runs, unbroken, from dark matter halos in the early universe to the molecular cloud that became this solar system, to the carbon and oxygen and water that constitute you. Each link in that chain depends on the one before. Without the dark matter halo, no disk. Without the disk, no generations of stars. Without the generations of stars, no heavy elements. Without the heavy elements, no rocky planets, no water, no chemistry capable of producing biological molecules. You exist because of something invisible. Imagine the universe without it, not a universe with slightly less dark matter. Not a universe where the dark matter is distributed differently. A universe where dark matter does not exist at all. None. A universe made entirely of the 5% of protons, neutrons, electrons, photons, and neutrinos in the proportions that emerge from Big Bang nucleosynthesis, and nothing else. In this alternate universe, the Big Bang still happens. The first 20 minutes still produce hydrogen and helium in the same proportions. The photon baryon plasma still oscillates through the same 380,000 years of acoustic waves. The fog still lifts. The photons still stream free. Now ordinary matter is released, free for the first time, to respond to gravity. But the gravitational wells are not waiting. There are no dark matter halos preformed over the hundreds of millions of years before recombination. There has been no quiet accumulation, no head start. The only density variations available are the same 1 in 100,000 fluctuations that were seeded in the early universe, tiny, barely there, present in the photon baryon plasma, but not amplified by any external scaffold. These variations must grow from essentially nothing in a universe that is still expanding. And they must race the expansion. Structure formation is a competition between gravity, which tries to collapse density variations into bound objects, and the cosmic expansion, which tries to dilute everything and separate regions of space from each other. In our universe, dark matter pre-deepened the wells deeply enough that ordinary matter could fall in quickly before the expansion could dilute it. The race was won decisively. In a universe with only ordinary matter, the initial density variations are far shallower. They have not been pre-amplified by the equivalent of hundreds of millions of years of dark matter accumulation. Gravity is trying to pull matter together from variations of 1 part in 100,000 with nothing pre-prepared. And it must do so before the expansion separates everything. The expansion wins most of the time. Cosmologists have run simulations of baryon-only universes, computer models that evolve the equations of gravity and fluid dynamics from the recombination conditions forward in time without any dark matter. The results are striking and almost unrecognizable as a cosmos. There is no cosmic web, no great filaments of galaxies stretching hundreds of millions of light years, no rich galaxy clusters containing thousands of galaxies. Instead, there are sparse, irregular concentrations of gas scattered through vast, nearly empty volumes, a universe that looks more like slightly lumpy fog than the intricate web revealed by the Sloan Digital Sky Survey. The Sloan Great Wall, which stretches 1.37 billion light-years in our universe, does not form. The Laniakea supercluster does not form. The rich, dense galaxy clusters that contain the most massive black holes and the oldest stars do not form. The elaborate filamentary structure of the real cosmic web, the structure that looks, in large-scale surveys, like a three-dimensional spiderweb of extraordinary delicacy and scale, is simply absent. If any galaxies form at all in a baryon-only universe, they form much later. Without the concentrated dark matter halos to draw in gas quickly, the collapse of gas into star-forming regions proceeds slowly against the continuing expansion. The first stellar generation, population 3, would form much later than the 100 to 300 million years after the Big Bang that current models predict for our universe. And the first star-forming regions would be smaller and less dense. The massive, luminous population 3 stars that are the universe's primary engines of heavy element production would be rarer and form later. Without the heavy elements from those first stars, the second generation of stars would still be nearly pure hydrogen and helium. More cycles of star formation and enrichment would be needed before the interstellar medium accumulated enough carbon, oxygen, silicon, and iron for rocky planet formation to be possible. Each cycle takes billions of years. In a universe 13.8 billion years old that has barely formed its first generation of galaxies, there would be no rocky planets. There would be no chemistry beyond the simplest hydrogen and helium reactions. No carbon, no water, no silicate minerals, no iron cores generating magnetic fields, no biochemistry. A universe without dark matter, at any epoch comparable to the current age of our universe, is still almost entirely hydrogen and helium gas, slowly cooling and diluting in an expanding void. Enormous, ancient, cold, empty of anything we would recognize as complex or interesting. Now, consider the stranger possibility at the other end of the imagination. We model dark matter as the simplest possible thing, particles that interact only through gravity, with no other forces between them, no dark chemistry, no dark structure beyond the broad gravitational halos that gravity alone produces. This is the minimal assumption. It matches the observations. The NFW halo profiles seen in simulations match galaxy rotation curves. The large-scale structure produced by gravity-only dark matter simulations, most famously the Millennium simulation run by Volker Springel and collaborators at the Max Planck Institute in 2005, and its successors, match the observed cosmic web with remarkable fidelity. But minimal doesn't mean correct. Our observations of dark matter are entirely gravitational. We observe its mass distribution. We observe its response to gravity. We observe nothing else about it, because electromagnetically it is completely transparent. Whether dark matter has its own internal forces, its own analogues of electromagnetism or the strong nuclear force, whether dark matter particles attract and repel each other through a dark force that operates only within the dark sector, whether there is a rich, dark chemistry of dark-bound states and dark transitions producing dark radiation, none of this is accessible to any telescope or detector we have built. Our gravitational observations constrain the total mass distribution. They say nothing at all about what that mass is doing internally. Some theorists have explored this possibility: a dark sector with its own forces, dark photons, dark electrons, dark nuclear physics could produce dark matter that does far more than form smooth halos. It could collapse into dark, compact objects. It could form dark analogues of stars burning dark fuel by dark nuclear reactions, radiating dark photons that only dark matter absorbs. In the most elaborate versions, there could be a dark periodic table, dark chemistry, dark complexity, an entire physical world coexisting with ours in the same space, governed by the same mathematics of field theory and quantum mechanics, but with different couplings and different particle masses, utterly inaccessible to any electromagnetic observation. These ideas are speculative. There is no evidence for them. They are not leading theories so much as legitimate possibilities in the space of physics we have not yet been able to close off. They are reminders that the standard model of particle physics, the most precisely tested theory in the history of science, describes only the 5%. It says nothing about the 95%. The equations that govern the interactions of quarks and electrons and photons were written to describe ordinary matter, because ordinary matter is what we observe. There is no reason in principle why the dark sector must be simpler than the visible one. The visible sector has dozens of particles and 4 forces. The dark sector might have 1 particle and 1 force, or it might have 100 particles and its own complex hierarchy of forces, producing its own forms of structure and history that we will never be able to see. But if any of them were correct, the dark matter halo of the Milky Way would be something very different from what we currently model. Not just a gravitational scaffold, an invisible world, dark structures of unknown complexity occupying the same spatial volume as the visible galaxy, passing through our stars and planets and our bodies without any interaction we could detect. Dark structures that might have their own history of formation and evolution, their own equivalent of the stellar populations and galactic disks and cosmic web that characterize visible matter. A parallel universe, not in a separate spatial dimension or a separate brain, but here, in the same space, in the same volume, in the same galaxy. Invisible, untouchable, unreachable by any means available to us, we would not know. We could not know. All we would ever see is the gravitational shadow. The universe is built on something we cannot see, and that something may be, in ways we cannot yet access, more than we have imagined. Now, as we finally approach the end of tonight's journey through the invisible architecture of everything, it is worth pausing in something that doesn't require a telescope or a detector or a mathematical formula. For all of human history, for every civilization that has looked upward at the sky with curiosity, for every astronomer who has built a lens or ground a mirror or pointed an antenna at the darkness, we have studied the universe by gathering its light. We built mirrors and lenses and radio dishes and X-ray detectors and gamma-ray telescopes. We launched satellites and sent probes to the edges of the solar system. We gathered photons from across the electromagnetic spectrum and used them to reconstruct an image of the cosmos. Every astronomical discovery ever made, every star catalogued, every galaxy photographed, every nebula mapped, every quasar redshifted, every pulsar timed, every black hole imaged, was a result of gathering and interpreting light. Everything this channel has ever explored is part of that 5%, the luminous minority, the rare, atom-built, light-emitting fraction of the cosmos. All of human civilization, all of human science, art, architecture, music, philosophy, wonder, generated by beings made of the bright 5%, directed entirely at the bright 5%. And from within that narrow, luminous fraction, we found the shadow of the other 95, not by seeing it, by reasoning about it, by noticing that things behaved as though there were more mass than we could see, by following that discrepancy with precision and care and mathematical rigor for decades until the case was overwhelming, by measuring the motions of galaxies in clusters, by measuring the rotation curves of galaxy after galaxy, by reading the acoustic peaks of the cosmic microwave background, by watching two galaxy clusters collide and seeing the mass in a different place from the gas, by building underground laboratories and waiting in profound quiet and darkness for a particle that has not yet come. Think about the path by which we got there. We found it first in 1932 in the motions of stars in the galactic disk, noticed by a careful Dutch astronomer who speculated quietly and moved on. We found it in 1933 in a galaxy cluster where galaxies moved 400 times too fast for the visible mass to hold them, noticed by a difficult Swiss-American astronomer who called it dark matter and was largely ignored for 30 years. We found it in rotation curves measured galaxy by galaxy, year by year, by an astronomer who had been told her numbers couldn't possibly be right, who measured 21 galaxies and published every one, and was proven to have been right all along. We found it in the oldest light in the universe, whose acoustic fingerprint could only be explained if invisible matter had been present and dominant since the first tens of thousands of years of cosmic time. And then we found it, most strikingly, most inarguably, in the aftermath of a collision 3.7 billion light-years away, where two galaxy clusters ran through each other at 10 million miles per hour. The gas slowed down, the mass kept moving, and you could look at the data and see plainly that the mass was in a different location from the ordinary matter, that something was there, that it had always been there, invisible and dominant, shaping everything around it. We found all of that without ever seeing a single dark matter particle, without ever touching one, without ever catching one in a detector. We found dark matter by understanding the shape of its absence, by noticing repeatedly over decades in different observations by different scientists using different techniques that what we could see could not be all there was. That is the kind of discovery science makes at its deepest limits. Not a photograph, not a direct measurement, a pattern in everything that surrounds it, an absence shaped like a presence. And what that absence reveals is this: the dark matter halo of the Milky Way existed before the first star in our galaxy ignited. It was there before the disk formed, before the spiral arms took shape, before the molecular cloud that would become our solar system had condensed from the interstellar medium, before the sun, before the earth, before the oceans and the atmosphere and the chemistry that eventually, on this particular rocky planet, gave rise to something capable of looking upward and asking what everything was made of. The halo was there, accumulating slowly over hundreds of millions of years before a single photon was emitted from a single stellar surface, shaping, pulling, building the gravitational architecture into which ordinary matter would eventually settle. It shaped what came after. The gas fell in along the gradients the halo carved. The disk formed in the equatorial plane of the halo's angular momentum. The spiral arms organized in the disk's density waves. Inside the arms, molecular clouds collapsed. Generations of stars formed and burned and died and enriched the interstellar medium with every element the periodic table contains. The molecular clouds grew richer. The conditions for rocky planets assembled over billions of years, and eventually, 13.8 billion years into a story that began invisible and dark and structureless, something assembled from the luminous 5% looked up at the sky and noticed that the darkness was not empty. We are made of the exception. We are assembled from the small, bright, atom-built minority of the universe. And we are here because the invisible majority spent billions of years building the conditions for the exception to come into being. It was there when the universe was 380,000 years old and the first light streamed free. It was there when the first stars ignited in the densest halos, hundreds of millions of years later. It was there when those first stars died and scattered the first heavy elements into the gas. It was there when the Milky Way began to take shape as a disk. It was there when the molecular cloud that would become our solar system condensed out of the enriched interstellar medium 4.5 billion years ago. It has been there at every step. Every atom of carbon in every cell of every living thing on this planet was forged in stars that formed in dark matter halos. Every drop of water in every ocean was delivered by rocky bodies that accreted in the disk of a solar system shaped by the gravitational environment of the dark matter halo. Every breath you have ever drawn has been possible because of a chain of events that began in the invisible. The universe is built on something we cannot see. And we, the 5%, the wandering fraction, the curious atoms looking back at the dark, are here because of it. Thank you for joining me tonight on this quiet exploration of dark matter, the invisible architecture of everything. If this journey moved you, or challenged you, or changed the way you see the darkness you move through, please take a moment to like the video and subscribe. It helps this channel reach more curious minds like yours, and it means everything to know you are out there, drifting through the invisible alongside us. Sleep well tonight. Good night.